Swayam Prabha. Digital India. Educated India.
Now, let us apply the concepts that we learnt in this week. For example, the displacement, what we mean by motion field, what we mean by deformation field, what we mean by traction, to solve some example problems. Example 1, what we are going to specify is the deformation field or the motion field, and we want to use this to find the displacement field. Now, let us say the deformation of the motion field is specified as x is equal to lambda 1 x, small y equal to lambda 2 y, and small z is also equal to lambda 2 z, where capital X, capital Y, capital Z represents the coordinates in the reference configuration. These are the coordinates of a typical material point in the reference configuration. And small x, small y, and small z represents the coordinates in the current or deformed configuration. We want to find what is displacement field u. We know that u is given by small x minus capital X. So, which will be substituting for small x as x E x plus y E y plus z E z minus capital X is capital X E x plus capital Y E y plus capital Z E z. Now, you substitute E z. Now, you substitute for small x lambda 1 capital X, small y lambda 2, you substitute for small x lambda 1 capital X, small y lambda 2 capital Y, small z lambda 2 capital Z. Then what you get is, get this as lambda 1 minus 1 into cap x E x plus lambda 2 minus 1 cap y E y plus lambda 2 minus 1 capital Z E z. Here I am assuming that the coordinate system used to represent both the reference and the current configuration is the same, which will typically be the case in many problems. Okay. So, this is the displacement field u written in terms of capital X, capital Y, and capital Z. So, this is called as the material representation of the displacement field Okay. So, now what is u x component? U x component would be lambda 1 minus 1 into capital X, u y component would be lambda 2 minus 1 capital Y, and u z component would be lambda 2 minus 1 capital Z. These are the components of the displacement vector, okay, represented in the material form. Now, say I want to represent the same displacement field in terms of the spatial form. Okay. I want to give a spatial representation for u. Spatial representation means, as we saw before in the lectures, displacement field means, as you saw before in the lectures, ux, uy, uz should be written in terms of small x, small y, small z are the coordinates in the current configuration. So, you know that the relationship between the coordinates in the reference, the current is given by this equation, and you know the components of ux, uy, uz in terms of the reference coordinates. So, you invert this equations to get the coordinates, the components of the displacement field represented in terms of the current coordinates, that is now ux would be lambda 1 minus 1. From this equation in here I can write, from this equation in here I can write small x, capital X as small x by lambda 1, right. So, I have replaced this capital X by, from this equation as small x by lambda 1. So, this is now in terms of small x here. So, this is a spatial representation of the displacement field. Okay. Similarly, uy would be lambda 2 minus 1 small y by lambda 2, and uz would be lambda 2 minus 1 small z by lambda 2, again coming from the definition of what the motion field is. Okay. In general, if x and small x, small y, small z and capital X, capital Y and capital Z are related through a linear equation, then you can write small x, small y, small z as some matrix times capital X, capital Y, capital Z, wherein this matrix will be F11, F12, F13, F21, F22, F23, F31, F32, F33. If the current coordinates is related to the reference coordinates through this equation, then you can write small x, capital X, capital Y, capital Z as inverse of this matrix F11, F12, F13 inverse small x, small y, small z, right. So, in this manner you can find what is the relationship between capital X, capital Y, capital Z and small x, small y, small z. Okay. Then you can write u as small x minus this, let me call this as F inverse matrix, this will be F inverse small x, small y, small z. So, this is the spatial form for u, the displacement field. Okay. This is how you compute a spatial form. Okay. In example 2, what we are going to do is, we are going to specify the displacement field and find the motion field or the deformation field. Okay. Here displacement field u say is given as kappa y. Now, let us assume the displacement field is given as kappa y Ex plus lambda 2 y Ey, okay, where y is y coordinate in the reference, y coordinate in the reference configuration. Now, I want to find what is small x, I want to find what is small x. Okay. From the relationship between the displacement and small x, you know that displacement is small x minus capital X, therefore, small x would be u plus capital X, right. Okay. Now, u is represented in the material form because it is in terms of the reference configuration coordinate system, okay, coordinates. Okay. So, directly I can add this up and I will get it as x plus kappa y Ex plus lambda 2 plus 1 y E y plus z E z, where this capital X is written as x E x plus y E y plus z E z, and this displacement field is from what is given, it is kappa y E x plus lambda 2 y E y. So, if I add these two, you will get this equation. Okay. Now, say I want to represent u in terms of the spatial form, I want to represent this u in terms of the spatial form, I want to represent this u in terms of the spatial form, then what should I do? I know that from here small x is x plus kappa y, small y is lambda 2 plus 1 capital Y, and small z is capital Z. This will imply, from this equation I can straight away write capital Y is small y by lambda 2 plus 1, and capital X is small x minus kappa by lambda 2 plus 1 into small y, substituting for capital Y from this equation in here, and small capital Z is nothing but small z. Okay. Okay. Now, having represented this, now it is easy to convert the material representation of u to a spatial representation of u as, now in spatial form u would be kappa y by lambda 2 plus 1 E x plus lambda 2 by lambda 2 plus 1 into small y E y, where I have substituted this equation for capital Y in this expression, where I substituted this in this equation to get this equation. Okay. Okay. Now, having understood what a displacement field is and how to represent it in the material and spatial form, the next concept that we saw was traction, okay, and stress tensor. So, let us solve some example problems involving traction and stress tensor. Okay. Example 3, say I gave you the stress tensor is of this form 10, 5, 0, 5, 0, 0, and I want to represent this using a plane stress square or rectangle. Okay. I do not want to go for a stress cube because it is in terms of a plane stress, one column and one row are zeros. So, I can represent it in 2 dimensions sufficiently enough. So, I choose my coordinate system to be E y, E x, and the rectangular element is drawn like this, infinitesimal rectangular element. I want to indicate what this 10 represents as a component of the stress tensor. Okay. You know that this 10 represents the sigma xx component of the stress tensor. So, sigma xx component is on the area whose normal is x, it is the direction of force is also x. So, this will be sigma xx, which is 10, it is in the positive direction because 10 is a positive number. Similarly, this 5 represents sigma xy, which means the area is acting along the normal to the surface is acting along the x direction and the force is acting along the y direction. So, which means this is 5, right. Okay. So, from equilibrium or otherwise, you know that this will be 10 and this is also going to be 5 and this shear is also going to be 5. Okay. This is the representation of the stress matrix or stress tensor into a figurative representation of the stress state. Okay.